Okay, so my name is Maria Ragnes, and it is my pleasure, together with my co-host today, Thomas Ruvik and Joachim Sinnes, to welcome you to the second seminar in our 2026 series of the Langtangen Seminar on Scientific Computing. Hans-Peter Langtangen was an exceptional mentor and supporter of research talents, so we thought it would be fitting that this year we dedicate the seminar series to leading voices of this and the next generation. And today's speaker is Professor Olga Mula Hernandez. Olga completed her PhD in applied mathematics at the LJLL at Sorbonne in 2014 and has since then held positions in Aachen, at Paris Dauphine, at TU Eindhoven, and is now a full professor and chair of computational PDEs at the University of Vienna. She's made fundamental contributions to optimal transport, to model order reduction, and how to understand the mathematical foundations of scientific machine learning. And I suspect that this is the topic she will speak on today, on gradient flows and neural networks. If you have any questions, as usual, please do write them in the chat, and Joachim will lead the Q&A after the talk. So with that, please go ahead, Olga.
Thank you very much, Mari, for the super kind introduction. And thank you, first of all, for the opportunity of speaking here. I think it's a very nice format, the one that you propose. Not a lot of talks, but quite selected somehow. Indeed, feel free to interrupt me actually at any time if there is any question. I hope that if I don't realize, Marie or Thomas will take care of it. And without further ado, we are going to speak today about a recent line of work that I have initiated a couple of years ago on solving PDEs using neural networks. So this is something that many people are doing, and there's a lot of activity. In my view, I am seeing still not that many papers in which we really explain how neural networks are behaving in the algorithms that we produce to solve these PDEs, and this is an attempt to really produce some mathematical theory that goes all the way down to an algorithm, and it really explains the behavior of an algorithm. So we are going to focus on gradient flows on Hilbert spaces. And so the goal is going to be the following. So I'm going to start my presentation by pasting a piece of text just to save a bit of time. Our goal is to focus on gradient flows that are going to be defined in the space L2. And we are going to have only one space variable, because in fact, to do the whole theory that I'm going to talk about, it is extremely challenging, and for the moment, we only manage to work in this space. So the gradient flows that we are going to focus on, they write like this. It's an evolution of an unknown u of t, and its dynamics, the time derivative is given by minus the gradient of an energy function f. And our goal is to solve this type of equations by using neural networks as an ansatz for the solution. Now, this type of approach that I'm going to speak about, it has by now actually many, many names, depending on the community in which one speaks about. So I come from the community more of numerical analysis, and the method I'm going to speak about is often called nonlinear dynamical approximation. Another name by now is called neural Galerkin. And if you go to communities more connected to machine learning, what I'm going to talk about is known as natural gradient. Now, the connection with machine learning in this talk is because when one wants to minimize a function in a Hilbert space, and one does a gradient descent approach, in fact, the continuous version of gradient descent is going to be precisely given by this type of dynamics, and the loss function in the optimization problem is going to be given by this energy function that I have written over here. So I'm going to first introduce the idea of the scheme. And in order to do this, I need to introduce a language to speak about the neural network. So this is what is going to happen in this first part, in which I am going to call all this decoder approach for a reason I am about to explain. Decoder approximation. Decoder approximation. So we are going to work in the following with the following language. There's going to be a mapping phi that I'm going to call a decoder that is going to take parameters from a parameter space theta to our ambient space V, which I remind you it's L2 of R in our case. So this function is called a decoder, and it can sort of represent a lot of different function approximations and function classes that we know. The one that we are going to focus on are going to be shallow neural networks. And in the language I want to establish, so a shallow neural network is going to be the mapping phi of theta, which is going to be evaluated at a point x, and this is going to be a linear combination of coefficients ci sigma aix plus bi, and theta here is the parameter, and it is going to be the family of ai, bi, and ci from 1 to n. So this is going to be a parameter in a space capital theta, which is going to be, in this simple case, 3 times n. Okay, so of course I can generate plenty of other different classes of approximation families by changing my definition of the decoder. And I'm calling this mapping a decoder because it is going from a finite dimensional space to an infinite dimensional space. And there's the jargon to express the opposite. Encoder would be a mapping that goes from a very high dimensional space to a smaller dimensional space. And so this is the reason why I'm adopting this type of language. Now, our strategy to solve the PDE is going to be that the solution u at time t of our gradient flow, we want to approximate it with neural networks whose weights are going to depend on time. And if we do this, in fact, what we are going to hope as well is that the time derivative of this is also going to be well approximated by the time derivative of the neural network that we are going to be using. And so by the chain rule, this velocity is just the differential of phi at the point theta of t and evaluated at the velocity theta dot of t. Now, when we are in R3, like in this example, just the differential here is very simply kind of replaced by the gradient with respect to theta of our decoder evaluated at the point theta t, then scalar product in Rn against a vector theta dot of t. And let's see in which kind of spaces these things are lying. So my phi here is going to be an element of a space V that I'm going to call Vn, which is going to be a subset of my ambient space, and Vn is going to just be the image of my parameter space under the mapping capital phi. So we have to imagine that we are going to be in our but drawing we have to imagine that we are going to have still a bad drawing. I would like that we imagine the situation as being in some space capital theta, and thanks to the mapping phi, we are going to go to the full Hilbert space V. And in this Hilbert space, there is going to be a subset which is going to be generated by Vn, the image of my decoder. And so what happens is that if I fix a parameter theta in here, if we understand the parameters as some sort of manifold, here it's R3n, but in general this could be a Riemannian manifold, there's going to be here a tangent space attached to this little element, which is going to be the tangent space at theta of our space capital theta. And this, via the differential map, it is going to send us here to the image phi of theta. And this one, we should also imagine that it has another tangent space, which I'm going to call here tan of var phi theta of Vn. Okay, so variations in the input parameters are going to induce variations in the output functions generated by the neural networks. And it is important to realize this because here my velocity, the approximation of my velocity lies in this image here, which is in this tangent space of the manifold that I am generating in my ambient space. So this thing is eventually going to be seen as an element of this tangent space of var phi of theta of Vn. So okay, so of the tangent space, sorry. So this is the exact definition of all these things. And so let's see why working with a neural network is an extremely complicated thing. So here in my picture over here, this picture is a classical picture of somehow a Riemannian manifold, which has a chart and so on. But there is something very evil happening with neural networks, which is that, in fact, the dimension of the output space here, it can vary depending on the redundancy. And so in a classical Riemannian manifold, in fact, the dimension of this space is going to be constant and independent of the base point where we are looking at it. And so this is going to make us require to kind of understand better what are kind of the properties of this manifold Vn and of their tangent spaces in order to have a proper kind of catch at addressing the problem of solving our gradient flow with the neural network. And so in order to make you feel what is going on, let us assume that we have this as a neural network. Exponential of minus x minus theta 1 squared plus exponential of minus x minus theta 2 squared, where the theta here are going to be these two parameters, and we are working in R2. So now, if we look at the tangent space somehow, yes, if we look at the tangent space of this function through Vn, in fact, we can quickly realize that this is given by the partial derivatives of phi with respect to the parameters. And so this is going to be, in our case, if I just differentiate with respect to these parameters, I'm going to get functions of this sort, exponential of minus x minus theta 1 squared, minus theta 2 exponential minus theta 2 squared. And so here comes the catch. So the dimension of this tangent space if θ1 is equal to θ2, we see that this manifold is degenerate. So this decoder over here, it is like a sum of two Gaussians essentially, and the Gaussians can overlap when θ1 becomes equal to θ2. In this case, somehow the manifold is kind of over-parameterized because I only would need one Gaussian to express the function that I am trying to approximate. And this translates into the fact that the dimension of the tangent space here is going to be equal to 1 if the two parameters are the same, and equal to 2 if they are different. And so you see that the dimension here of this tangent space differs from the one of the original parameter space. And so this is something which is connected to the overparameterization of the manifold, and which is going to make the working in this type of setting very challenging. So I'm telling you all this because here's now the drama that is gonna happen when we try to do natural gradient descent. So the strategy is that we want to find a curve theta that depends on time, and that goes to our family of parameters, such that at every time somehow the velocity of our neural network approximation is approximated at best. And so this is going to be expressed as follows. So we want that the velocity of our neural network is approximated, is in the, let me write this and I will comment on this. It will be in v dot plus grad of f of phi of theta t. And this v dot is going to be in the tangent space of phi of theta t of Vn. So the rationale behind this is that we said that u dot t is equal to minus the gradient of f of u of t. And therefore, when I have the exact solution, if I look at the residual is going to be this thing. This is going to be equal to 0, right? So now I am building an approximation of the velocity with something that is generated by the neural network. And because it is a velocity, it is belonging to this tangent space of the manifold that I introduced. And I am sort of searching the element in this tangent space that minimizes this residual error. And this is going to be the best that I can somehow hope to find whenever I go with this approach. Because in general, of course, u of t is not going to be exactly equal to a neural network, and I cannot hope that that the residual is going to be equal to exactly 0. So the necessary conditions, the optimality conditions of this if we do the computation, in fact, we are going to end up with the following. We are going to end up with an ODE in the parameters theta that we are searching equals to a vector q of theta t, where m of theta t is going to be the matrix of scalar products of the partial derivatives of the phi I evaluated at theta t and the partial theta j of phi. And this is gonna go from 1 to 3n parameters that I have, okay? And so this is a vector, Q of theta t. It's going to be a right-hand side, which is going to involve like our gradient. Okay, so the issue I would like to raise is that, okay, so if this is this ODE, this is an ODE for theta t. And so if I manage to solve it, then the strategy is that I time integrate. Then I get my theta t. And then I get my phi of theta t, which will approximate u of t. But so here's the problem. The problem is that because the manifold that I introduced is over-parametrized, then this matrix over here, the M, it is sometimes going to become non-invertible. And this is because these partial derivatives with respect to theta I and to theta j, in fact, sometimes they become linearly dependent. This is what happened to us in the previous example over here when theta 1 was equal to theta 2. The span of these functions, it becomes only one function, and they become linearly dependent. And this makes that this matrix here is not invertible. And the issue is that therefore, because of this, the existence of solutions to this ODE is no longer guaranteed. We cannot sort of really solve this problem. So now, like the usual workarounds for this, the usual patches, I would say, are through regularization. Roughly speaking, what is going to happen is that here in my, if I come back to my optimization problem, I am going to add an extra term, an extra regularization term of this form, essentially, which is eventually going to lead to my optimality conditions being modified, and I am going to add some epsilon times identity to the matrix, and automatically this is going to become invertible. The problem with this is that we somehow lose the connection with the infinite dimensional operator that we wanted to solve. And there's also problems with like the time integration, the interplay between the time integration, the epsilon, and the connection with the original problem we wanted to solve is lost. So here is somehow the approach that we have developed in order to overcome this and come up with an understanding of what's the situation, which is kind of proper at like the functional level. And that leads to an approach which is also like an algorithm that is behind all this. So that's our contribution. So this is an approach through gradient flows in a metric space. So here is an approach that is going to successfully lead to something. We are going to view the space of neural networks when the parameter vary. So we are going to view Vn as a metric space. In order to do this, in fact, we need to endow this set with a certain distance. And in fact, the distance between two elements is just going to be inherited from the ambient distance in the Hilbert space. So this is just going to be the L2 distance from from in L2, okay? And so this is going to say that we are not interested in the values of the parameters to quantify how different two functions are. What we want to compare is like at the functional level, if two functions from the neural network are really kind of generating the same function in L2 or not, independently of whether they were generated by different theta 1 and theta 2, okay? So that's kind of the catch. And so we can prove that this is a metric space. And then the task is to define an evolution in this metric space, which is closely related to the original one in the Hilbert space. Okay, so that's like the task now is to define a gradient flow on this metric space. And so for this, you open what is called the Green Book by Savare, Ambrosio, and so on. And then so you go crazy for, in my case, I went crazy for about 3 or 4 years. Actually, I've been working on this problem. Eventually, you call some big person in the field because we couldn't really solve the problem on our own. So this is why Marc Pelletier was instrumental in helping us really find the final way. And so you learned from all this literature that already exists that one way of defining a gradient flow is through what they call minimizing movement schemes. So it turns out that if I come back to my previous formulation here, which I said is wrong somehow, there are a couple of reformulations of the optimality conditions, okay? All of them are going to lead to some sort of evolution equation in the end. One of these reformulations, if one does an implicit Euler discretization of the resulting optimality condition, one is led to the minimizing movement of our metric space. So we are going to introduce here a minimizing movement scheme, which is going to be as follows. So at time n+1, so I'm going to introduce a time discretization. Okay, and so the solution at time n+1 is going to be approximated by gradient flow in this setting, which is going to look as follows. So once you think about it, it sort of feels quite reasonable. So we are going to do, sorry, this is V in Vn of V, the previous time step, plus our energy functional phi of, sorry, I'm going to write here V as well. Okay, so this is a minimizing movement scheme in the gradient flow defined by the set Vn and by the distance d that I introduced before. And what happens is that it becomes difficult, but we managed to do this. One can show that when the time step here is taken to 0, the limit has a meaning, and it has the properties of a gradient flow, namely that we have some energy dissipation principles. But now everything has to be rewritten, not in the language of a Hilbert space, but in the language of metric spaces. And so the conditions, they need to be adapted and so on. And one challenging, I would like to mention here 2 challenging things. In order to define this evolution on this metric space, in fact, when you study the results by this book by Ambrosio and so on, the results are always phrased on metric spaces which are closed. Okay, and so the drama here is that the first drama is that Vn is not closed. Okay, this is because if you think about it, when the weights of the neural network theta, they are becoming very large or very small, and there are some combinations of them which are going to make us land to functions that are not in Vn. Okay, and Vn is not closed, and therefore we need to define the closure of Vn with respect to the L2 metric. And so this was quite a challenging part of this work, which, by the way, the work is not out. We are writing the paper right now. We need also to define tangent spaces on the closure. And somehow we need that all this is explicit, with explicit formulas, not with vague statements. We really need formulas. So we need explicit characterizations. Okay. So that's the first big challenge. And then the second big challenge is that in this game of gradient flows in metric spaces, one needs to define an appropriate notion of the energy functional, and also of some notions of gradients and slopes are involved. And so the second challenge is that we need to find what is called an appropriate strong upper gradient. And thanks to this, if we identify this notion of a strong upper gradient, then somehow the whole theory of these gradient flows in metric spaces is unlocked to us, and we can guarantee existence of solutions in this metric space. And we can therefore guarantee that this algorithm over here, in the limit when the time discretization goes to 0, that it has a meaning, that the energy is decaying, and that everything behaves as actually we expect it to behave. Okay. And so thanks to this, we are going to cure a lot of instabilities that appear in the classical approach. In the classical approach, everyone goes through this approach. And because we cannot invert the matrix, at some point, one is going to pay the price with some strong instabilities. In numerics, when this is not invertible, the computer is going to compute some pseudo-inverse, but at some point also this pseudo-inverse is gonna kind of go south, and we are going to see some instabilities. I would like to show to you these instabilities, but for this, I need to kind of change and share my screen with the other login that I have. I'm sorry about this. I'm gonna try to do the change. Can I do the change? Stop my sharing over here. I am going to share my other screen for this. Could you please confirm that you can see my screen?
Yes, we're all good. Thank you.
Thank you very much. So what you're about to see is one simulation in which this bump is going to go down and then it will become negative. In another simulation, this is a gradient flow, and the simulation is going to go down as well, and the bump will go negative, but it will be shifted. The one with the shift is computed with the classical naive approach, so to speak. The one without the shift is produced by the minimizing movement scheme. And it can be shown that if you shift, like with the wrong naive approach, then the solution that you're producing is not dissipating maximally the energy as you should. So here we go. This is, so both are kind of looking okay, but at some point, one up, oh, it went very fast. Sorry about that. I'll stop them when they have to. We see that this one, the bump has sort of shifted. In this left one, the bump is going to stay in place and go negative. There we go. So here the bump is at the level of between 1 and 2. Here the bump is in the negative numbers as well. We can show that the shift in the bump is unphysical, and this is not a gradient flow. And so we are somehow solving the wrong dynamics. And all this is produced by the non-invertibility of the matrix that I was telling you about. So here is another example, which is also quite striking. If we now look at this evolution, which is an Allen-Kahn equation, it's an L2 gradient flow. What you're about to see is the following. Let us make this evolve. At some point here, if you see in this region, the true solution is in blue, and it is having this kind of valley. The neural network solution with the naive approach, it was doing well until at some point it immediately jumped. So this kind of instabilities are created by the non-invertibility of this matrix. I'm replaying here. There, it really jumps. And there's a discontinuity because of this problem. So I'm going to stop the share, and I will continue maybe just orally without any document now. This concludes my talk. I would like to highlight that what I like about this result is that thanks to it, for example, we have started giving explicit expressions of closures of the family of neural networks. This is important because when we do optimization, for example, the weights, they become very large, and we need to kind of understand how to deal with this properly. And so if we have an explicit characterization of the closure, maybe it means that we can use this explicit characterization to sort of avoid this very large weights and directly use the elements in the closure. The second thing that I like about this result that brings knowledge is the fact that we are sort of really producing a theory that can be very directly connected with an algorithm for which we have guarantees that it is going to behave in a proper way. And so I feel that now, in connection with maybe giving elements of how maybe we could hope that the field evolves, I think that if we managed to start producing more this kind of results, where really a very kind of deep mathematical result can be somehow leveraged to solve problems that we identify, that would be great. So for the moment, I feel that there are very little results because it's really very hard. It has taken us about 4 years actually to derive this result. We need some patience, and also somehow the ecosystem is kind of putting us in a hurry in producing papers. I hope that we can get more patience and that we can really start streamlining and not only kind of producing nice pictures and nice patches to things. That's what I hope that the field is going to strive for. This line of research about these neural networks where the weights depend on time, I consider it is very promising to solve not only gradient flows, but plenty of other different dynamics. And it is, I think, going to bring a lot of knowledge on the class of functions of neural networks themselves. For example, this example of the closure is one example. Another thing that I feel that is going to be very exciting to work on is to see if all these results that we kind of prove with pen and paper, so to speak, if we could not start implementing them in proof assistance such as Lean and so on, so that the proofs are completely validated and that they can be taken off the shelves by other researchers. So I think that these directions are, for me, very exciting. I think I will stop here, and I hope it will trigger some discussions. I'll be happy to answer to some questions.
Thank you very much, Olga, for a very nice talk and for sharing your thoughts. I'll give the word over to you, Joachim.
Yes, thank you. I agree. This was a very good talk and very interesting topic. I see one person with a raised hand, and that's Thomas. So I think I'll give him the word to ask the first question.
Yeah, thank you, Joachim, and thank you, Olga, for this nice lecture. I too struggled with the Green Book quite often in the past, and I was curious if you can actually elaborate a bit on how you find this strong upper gradient, like a concrete computation of this object.
Yeah, indeed. I am very happy to show this to you offline.
Okay,
For
this is
this
not
for this
yeah.
talk,
Mhm.
it is going to take me a few minutes.
Mm.
The real difficulty that we hit was that in this literature they have a lot of different notions of gradients. They have the strong upper gradient, the weak upper gradient, the relaxed slope, the strong slope, and we could not find our way anymore through this. And this is where the expertise of someone from the field really came in. And to give you a hint on how it is built, we take like the original energy function. And in fact, we are going to make a restriction of it into some set connected to the neural network manifold, but in a very kind of elaborate way, which would take me several minutes to explain.
Yeah.
So yeah, it was really, I found it very hard. This was done, by the expert Marc Pelletier, our collaborator. And one difficulty also is that the usual candidate for being the upper gradient has to, I mean, the upper gradient has to be lower semi-continuous. And in the context in which we are working with the variety of energy functionals that we are dealing with, it should not be expected that this one can be lower semi-continuous. Then it means that you need to introduce the lower semi-continuous envelope and then go even fancier because you need to restrict it to some fancy set. So yeah, I will gladly tell you offline the details.
Yeah, okay. So it's highly non-trivial, I guess, as I
Yeah,
suspected.
yes, I would say so.
By the way, what's the reason for having to restrict to L2 on just the reals as opposed to L2 on, I don't know, Rn?
Okay, yeah, I forgot to specify this in this talk. You remember I have introduced shallow neural networks.
Yeah.
So our result actually works for shallow neural networks with certain strong restrictions, actually. One of the strong restrictions is that there are dilates. There are this sigma A I X plus BI.
Yeah.
Our result, we don't know how to do the result with the AIs, the dilations. We need to remove this as a parameter, and so we only kind of consider shifts and linear combinations of an activation function.
I see.
And yeah, so in the beginning, we were finding it so difficult and so confusing that we have done the result in 1D, and this is how we are very probably going to publish the result. I think that if we don't add these dilations, the result can be generalized to multi-D in L2 fairly simply. Now, the next steps are, to add the dilations and to consider other spaces as well.
I see.
And so for the dilations, we consider this highly non-trivial. We don't know. And what we don't know is what is the closure with these dilations.
Yeah, that makes. I mean, I don't know why the dilations are so complicated because I haven't seen the details, but I can understand why the closure is an issue, right? Because I've seen that elsewhere where people have done kind of like a Ritz-Galerkin type of discretization of, let's say, an energy minimization problem where you replace the Sobolev space by some space of neural networks, but then that's not closed in the Sobolev space, and so to even have a solution, right? That's kind of the question that arises. Okay, I'm sorry, I have to run to. Thank you so much. It was nice seeing you. Bye-bye.
See you.
Yes, we have a couple of questions in the chat here as well. First one is from Baltasar Beferul Lozano. It's a long question, so I'll try to read it as correctly as I can. You mentioned the challenge that the Hilbert space Vn is not closed, which implies that the continuous gradient flow could theoretically leave the space or fail to admit a limit point within it. If you resolve this by taking the metric completion of Vn, what is the practical interpretation of those limit points? Do the idealized networks in the closure but outside of Vn correspond always to recognizable pathological states like infinite weights or collapsed neurons?
So in the limit, in our very simple setting for the closure, we see that the elements, they are not coinciding with our original neural network, and it means that in practice there's a very interesting situation or challenge that is going to arise. How can we add them and take them into consideration when we are doing the training? This is, for me, actually a very exciting question. And I think that the person asking it is kind of concerned about this. My answer is that at the moment, I don't know how to use it. For all practical purposes, what we have been observing is that, so the waves, they can go very high. And at some point, they can go very high also in our minimizing movement scheme, meaning that it would be useful if we could incorporate these elements in the closure. For the moment, we have not done it, but it would be very nice to do it. Even with very high weights, we observe that the solutions produced by the minimizing movement, they are much more meaningful than the other ones from the naive approach, but still there's plenty in numerics to do.
Thank you. I have one second question that's also from Baltasar. It's also a fairly long one. So it says, he writes, I understand that finding a strong upper gradient is critical for establishing the energy dissipation identity in your framework. Given that deep neural network loss landscapes are highly non-convex and lack standard regularity, what structural assumptions are you hoping to rely on to construct this strong upper gradient? Are you looking into specific generalized functional inequalities like local Lipschitz bounds to guarantee its existence?
So on top of my head, I don't fully recall the conditions that we have on F, but I would say that in fact that's not really a big issue for us. I think that the F can be non-convex, and we will fully benefit. I mean, we can just plug our neural network closed set. We can plug it into the theory of Ambrosio et al. Without F being convex or without having very strong assumptions on it. I would like to kind of emphasize, I think we have some mild assumptions, but I don't really remember them now on top of my head.
Yeah, fine. Thank you. And I think there are no more questions in the chat. So I think I'll just give the word back to Marie.
Thank you, Joachim, and thank you again, Olga, for this seminar. It's been our pleasure, and thanks to all participants. And I'll stop the recording now and wish you all